and everyone who uses the book will remain ignorant, unfortunately. I speak from personal experience. I used that book too when I was an undergraduate, and I didn't know anything. When I got to grad school, it was a bad thing. But anyway, so this is straight up the formula for the function near the critical point. It's so that the variability of it is completely governed by what? A quadratic form, right? So what happens with this is we can rewrite this, right? We can rewrite this piece as lambda 1, right, times h bar 1 squared, right, plus lambda 2 times h bar 2 squared. And let's think about this. If both of the eigenvalues are positive, f of AB is a what? Think about this. If they're both positive, as you are near the point of the critical point, you're adding to the value, which means that your f of AB is a local minimum. If both of the eigenvalues are negative, you're taking away from the value at AB, so you're at a local maximum. If one eigenvalue is negative and one eigenvalue is positive, then you're at a saddle point, because some directions you're increasing and some directions you're decreasing. All right? Those conclusions are immediately clear from this formula, right? I'll put the half out here. The half doesn't change anything, right? So what's the formula for the eigenvalues of this matrix? Can you guys tell me? Can we work that out? Let's work it out, right? What's the determinant of fxx minus lambda fxy, fxy, fyy minus lambda, right? That would be the characteristic equation for this matrix. By the way, this matrix has a name. This matrix is called the Hessian matrix. So what we got is fxx minus lambda times fyy minus lambda minus fxy squared, yeah? Let's work this out. So we got fxx, fyy, right, minus fxx plus fyy times lambda plus lambda squared minus fxy squared, yeah? In other words, we've got lambda squared minus parentheses fxx plus fyy times lambda plus fxx fyy minus fxy squared. Now, we don't actually need to solve this characteristic equation. We should be smarter than that. Like, what's the deal with the characteristic equation? If we think about it, let's call this P of lambda, right? P of lambda has what form? It has the form lambda minus lambda 1 times lambda minus lambda 2, right? So that gives us what? Lambda squared minus parentheses lambda 1 plus lambda 2, lambda plus lambda 1, lambda 2, right? So what's the product of the eigenvalues equal to? Can you guys see it? I said go away. Go away. Get. Thank you. This right here is the constant term. This right here is the constant term. Right? It's also the determinant of the Hessian. So what we have is that lambda 1 times lambda 2 is equal to, fxx fyy minus fxy squared. What do we call this? We call this big D. It's the big D. And Stuart, it's big D. So check this out. D positive means that both lambda 1 and lambda 2 share the same sign. Right? You can't have the product of eigenvalues positive unless they're both plus plus or both minus minus, right? Okay, so case 1, if lambda 1 and lambda 2 are both positive, then we have D greater than 0, and f of AB is what? Local minimum, as I was explaining the logic of a second ago. And number 2, if we have lambda 1 and lambda 2 both negative, then again, we're talking about the D positive case, and f of AB is a what? Local maximum, because we would be subtracting from the value of the function at AB if we go away from AB. So that makes it a local maximum. If D is negative, what does that mean? If D is less than 0, then, lambda 1, either lambda 1 is greater than 0 and lambda 2 is less than 0, or you have lambda 1 less than 0 and lambda 2 greater than 0. In either case, you're looking at a saddle point, because in eigencoordinates, you can either increase or decrease depending on which direction you go. This is the second derivative test in Calculus 3. Right? What's the other case? It's equal to 0. What does the theorem say then? It tells you nothing, right? And that's because if D is equal to 0, what that means is that there's some eigendirection in which the quadratic piece doesn't have to be dominant. The cubic piece could play a role there. See, because past this, and this is plus dot dot dot, my friends. And the plus dot 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 there is cubic or quartic terms in the partial derivatives. And so if you've got 0, then it could be that the cubic term is the next one that plays the role of maximizing and minimizing. Or maybe the cubic is 0, and you got to go all the way to quartic order, fourth order, to see what wins. But so the reason that we can find a formula in Calculus 3 that's so nice and cut and dried is because it's a 2 by 2 matrix. And the eigenvalues for a 2 by 2 matrix, they're pretty well tied down to the components. Let's just take a step back and just play with that for a second. What are the eigenvalues of a 2 by 2 matrix? How do they relate to the entries? Do you guys know? You ever thought about this? Just thought about this? So if I've got the matrix A, B, C, D, what are the eigenvalues? How are those related to the entries in the matrix? There's two things. There's two simple equations we know for a 2 by 2 matrix that govern the entries of the matrix as they relate to the eigenvalues. Those two equations are trace and determinant. I was just talking to you guys in the derivation that we just looked at about determinant. The product of the eigenvalues is the determinant of the matrix. So it is true that lambda 1 times lambda 2 has to be equal to the determinant of A, which of course is AD minus BC. But we also know that lambda 1 plus lambda 2 is equal to the trace of A. And that here would be A plus D. So what you're looking at is two equations and two unknowns. Your two unknowns are the eigenvalues, right? So like, you know, if I had A equal to 2, 3, 3, 2, for instance, I would need lambda 1, lambda 2 is equal to, you know, 4 minus 9, which is minus 5, right? And I would need lambda 1 plus lambda 2 is equal to 4. What are the eigenvalues? What's that? You said lambda 1 is 5, and lambda 2 is what? Negative 1? Well, I mean, but make a choice, fine. Would that work? Oh, yeah, fair enough for our notation. Very good. And by the way, I talked about the spectrum. What is the spectrum of the matrix? The spectrum is the list of eigenvalues from lowest to highest. That's why we call it the spectral theorem. The significance of that is that we used to think about operators in connection to quantum mechanics, and the spectrum was literally like the energy values of the operator, if you're thinking about it as a Heisenberg energy operator, and that connects to like the study of spectroscopy and stuff. That's where these words came from. But yeah, I didn't see it, but you guys saw it, right? Why don't we teach a min-max theorem in calculus 3 for functions of 3 variables? You have a 3 by 3 matrix. You're looking for 3 eigenvalues, right? How are the eigenvalues of a 3 by 3 matrix related to its entries? The determinant is the product of the eigenvalues. The trace is the sum of the eigenvalues. Still true, but that's 2 equations and 3 unknowns. And there simply is no nice cut and dried simple formula for the eigenvalues, right? Like, well, I guess more generally, if you think about the determinant of the Hessian matrix in the 3 by 3 case, you'd have like lambda 1, lambda 2, lambda 3, right? And I suppose there is a theorem to be said there. If all of the eigenvalues are positive, then it's a minimum. If all of the eigenvalues are negative, you know, it's a maximum. But there would just be a lot more cases, and it wouldn't make a nice theorem that you could tell calculus students. The better answer is learn linear algebra. You calculate the Hessian matrix, you diagonalize it. That shows you the nature of your critical point. If all the eigenvalues of your Hessian matrix are negative, it's a maximum. If all the eigenvalues of your Hessian matrix are positive, it's a minimum. And if all the values of your Hessian matrix are a mix of positive and negative, it's a saddle point. That idea works in n dimensions, and that's what I teach in advanced calculus. And that's why I make linear algebra a prerequisite for advanced calculus here, because I actually form the union of calculus 3 and linear algebra in that course. But anyway, I shut up. That's all for today, guys.